Right, so we were looking at a pressure in fluids question. So an aquarium is filled with salt water of density 1020 kg per meter cube. It is 10 meters deep. The bottom of the aquarium is to be filled with a glass window of measurement 2 meters by 1.5 meters. The atmosphere above the water surface is 101 kilopascals. They want us to calculate the pressure, the total pressure, and the maximum force that the glass should be able to withstand. So Shayna, do you understand what I'm saying here? That if you have something submerged in a fluid, as a result of the fluid is going to press down on whatever is placed in the fluid, and as a result, you're going to have a pressure acting on whatever you put inside here. That makes sense?
Yes.
What's gonna happen if the height of water is more? Would the pressure be less or would the pressure be more? What do you think?
If the height is more, the pressure will be more.
You said that the pressure would be less?
More.
More, right? Because when you think about it, wouldn't there be more vertical water pressing down on the object?
Yes.
Great. So anytime you're dealing with pressure in fluids, the formula that you need to remember, right? So pressure is equal to the height of the fluid by the density of the fluid by gravity. So the atmospheric pressure here is what? What's the atmospheric pressure in this question? Do you know the atmospheric pressure in this question?
It's 101 kilopascal.
Right, it's 101 kilopascals. So I'm going to write that in here, right? So the pressure in the atmosphere nice. And so they want us to find the pressure of the water acting. So that first part, they want us to figure out the pressure in the fluid. So we have to use the formula P is equal to H by rho by G. Can you tell me the height?
10 meters.
Right, because it's 10 meters deep. So on the diagram, I'm gonna add in this part here, 10 meters. Nice. What is the density?
1020.
Right. And what is the acceleration due to gravity?
You could use 10 or 9.8.
I will use 10. So when you work this out, you should get 102,000. So 102,000 pascals. You got that?
Yes.
Okay, cool. The total pressure.
It will be atmospheric pressure and the pressure you got from the water combined. So added.
So that'll be equal to 102,000 plus 101,000. Because it's kilo. So kilo means 1,000. So that's 101,000. So you understand that?
Yes, sir.
All right. When you add up those together, you should get 203,000. Did you get that?
Yes.
Cool. They want us to figure out the maximum force in kilonewtons. Oh, watch. In part two, they wanted the answer in kilopascals, right? So when we write in this answer, we're not gonna leave it like this. We should write it
It
as
will be
103.
403 kilopascal.
Yeah. You have to read the questions carefully because you gotta lose a mark like that. Right? So be very careful with when you're reading the questions. Okay, they want us to figure out the maximum force. What formula do you know has pressure and force on it. And wait, not just that. Look at what they give us. They give us dimensions. It sort of looks like we could use that those. I mean, it sort of looks like we could use those dimensions to find area. But think about it. What formula do you
So
know?
pressure equals force per area.
Right. You see how there's like this spoon feed here, right? Anytime you don't know what formula to use, just look at what you found previously and look at the extra information they gave you. So pressure is equal to force all over area. So we actually need to find for force. So we need to make F the subject of the formula. How are we going to do that? Tell me, Sheena, how am I going to make force the subject of the formula?
Multiplying both sides by E.
Right. When I do that, I'm going to get P E is equal to F. Then I could just switch around. My pressure is 203,000. And how am I going to find my area?
It will be 1.5 by 2, which is 3 meters squared.
So when you work this, when you work all of this out, you should get 609, and they wanted the answer in kilonewtons. So that'll just be
Okay.
609 kilonewtons. Why am I saying that? I'm saying that because when you work this out, you're gonna get 609,000, right? Which is the same thing as 609 kilonewtons.
Yes,
Understand
sir.
that, right?
Mm-hmm.
Great. So we did this question. Lovely. Look, even them made a mistake. Watch. It says in kilopascals and they wrote it as.
Okay.
All right. So we essentially covered the pressure in liquids, right? And you understand at different depths, what would happen is the pressure would increase, like depending on how deep it is. Because
Yes, sir.
if you are deeper, then there's going to be more vertical mass acting down on you, right? Gas pressure measurement. So barometer. No, that is not a rum shop. It's a it's a barometer. It's used to measure gas pressure, in case you were thinking that. So give this a read for me.
The atmospheric pressure acts on the mercury in the reservoir container, applying a downward force to it.
Mm-hmm.
We will continue. The mercury is pushed up the bore in the middle and forms a ring. The higher the column has, the higher the pressure. Mercury is used instead of water because of its high density. Mercury is 13.6 times denser than water. This means that if water was used instead, the column would be 13.6 times taller.
Right. So let's try to understand what's going on here. So inside this, we have a vacuum, right? We have mercury. There's atmospheric pressure pressing down on this, right? So let's try to understand what's happening here. So Sheena, when we place this vacuum here, and hence we could agree that this vacuum, when we initially place it, it would have nothing inside. It would have nothing inside this, right?
Yes,
But when you place it inside this, at first it will look as though it's the same level as the mercury, right? You with me so far?
yes,
But we must not forget that there's atmospheric pressure pressing down on this. If there was no atmospheric pressure pressing down on this, then inside the vacuum, it would be exactly at the mercury level. But because there's atmospheric pressure, it's going to rise a bit above. You understand that?
yes.
Yeah. So that's why you're seeing here, it's above the mercury level. And another thing, you would have seen them mention that mercury was used because it's much denser than water. if it's much denser than water, wouldn't the pressure be a lot more than if it was water inside this?
Yes, sir.
Yeah, because the density of mercury is 13,600 kg per meter cube. Do you remember what it is for water?
Density is it 1,000?
1,025 to be specific. So it's
Okay.
a lot denser. So like you have the atmospheric pressure here, and you also have the pressure as a result of it having a height. So all that is going to act and push it upwards. So again, that's why if they ask you to explain, if they bring a question like this and they ask you to explain why this is higher than the mercury level, you would say because the atmospheric pressure and the pressure as a result of it being a fluid and it having height, they press down, and so the total pressure presses down on the mercury and it causes that mercury to be pushed up into the vacuum. That's essentially the explanation in like really, really simple terms. So that makes sense, right?
Yes, sir.
Right. So atmospheric pressure is given as 760 um SOC millimeter Hg. Okay. But what is its value in pascals? Let me see. So pressure is equal to density. We know that the density is 13,600. We know that the gravity is 10 and 0.76. And they get that from over here, right? They got that from over here. 760 millimeters is 0.06 meters. So the pressure is 103,360. So that's the pressure. That's the pressure this is experiencing. You understand?
Yes, sir.
Okay, good. Have you ever heard of a manometer?
I don't think so.
Never?
Mm-mm.
All right. Give it a read from now. And then I'll go explain it.
Manometers are used to find pressures of fluids of interest. It does this by making a comparison to atmospheric pressure, which is already known. Atmospheric pressure is given as either 760 millimeters Hg or 101 kilopascals.
Right?
Oh, sorry, the difference in height of the column is used to calculate the pressure of the gas.
Right. So let's try to understand what's going on here. So, Shayna, do you understand that the atmospheric pressure would press down on the fluid and it would make the fluid want to like go down. That makes sense, right?
Yes, sir.
Okay. So stay with me. They would put a unknown pressure here. So like um it would have an unknown pressure here, right? It'd have an unknown pressure here. So the mercury would be inside of this, and under normal circumstances, if there's no unknown pressure, what do you think is supposed to happen? Do you think it should be uneven, or do you think it should be both be leveled if there's no unknown pressure acting on it? What do you think?
It will be even.
It would be even, right? And that would be the case if there's no unknown pressure acting on it. Because if there was no unknown pressure, this would be open as well. So the atmospheric pressure would be acting on both sides. So it'd be even. But we're clearly not seeing that. So think about it like this, right, Shina? Initially, both of them would be at the same level. But because we're introducing an unknown pressure, this unknown pressure is going to press against this end, and that is what's causing it to go up. That makes sense?
Yes, sir.
Okay, good. But yeah, I agree that if it was open to the atmosphere, this side was open to the atmosphere, it would have been at the same level. But because
Yes.
we have unknown pressure, and this unknown pressure seems to be very high, it's pressing down on this fluid and it's causing it to rise. And that's the explanation for why it's uneven and there's a height difference. Because the two pressures are not the same.
Yes.
All right, then just by looking at this, which pressure do you think is higher, the atmospheric pressure or the unknown pressure?
Unknown.
Yeah, the unknown, because it will be pushing downwards, right? If the difference in height of both columns is 30 millimeters, what is the unknown pressure in mmHg? I don't know what is mmHg, but we don't ever use that in physics. Like the SI unit for pressure is pascals, right?
Okay, sir.
So pressure is 760 plus 30, and I presume this is measuring pressure in terms of the height difference of the mercury, because Hg is mercury. Presume so. So the pressure will be
Okay.
760 plus 30. So the pressure of this will be 790 millimeter Hg. And that makes sense. Let me show you why that makes sense. Um, if we say now this unknown pressure here is 790 mmHg, then that would explain why the height difference is 30 millimeters. So this measurement here, mmHg, just tells you, it tells you the height of the fluid. It tells you the height of the fluid, if that make any sense. Because like, watch this, right, Sheena? Watch this. If we see that this has a pressure of 790 mmHg, and this has a pressure of 760 mmHg, what's the difference?
30.
30. And the reason for that is because this pressure would cause this fluid to move up by 790 millimeters. That's what's happening. Whereas this one will push it up to 760 millimeters. So, Shina, try to understand that. If one of them is causing the fluid to be pushed up to 790, and the other one is causing it to be pushed up to 760, wouldn't they cancel off and it would leave you with 30 millimeters remaining?
Yes, sir.
You sure you can visualize that?
Yes, sir.
You're saying yes, sir, like this is real obvious. I just want to make sure you understand this.
Yes, sir, Sam.
Okay. Part two now. What is the unknown pressure of the gas in pascals? So again, we know that P is equal to H rho G. We know that, right? What do you think I'm going to use for my height?
Um, D 790, but in
I
in
don't,
Celsius, um, um, 0.79.
mm-hmm. I know what you get.
Wait, what was it?
Yeah, when you work out the whole thing, you should get 107,440.
Yes, sir.
And what if I ask you the pressure difference in kilopascals? How would you do that? Remind me, what does 760 mmHg mean in kilopascals?
0.76.
Nah, in kilopascals, that means 101 kilopascals.
All right. Oh,
Right. So Sheena, this is the this will always be constant, right? Anytime we're talking about atmospheric pressure, it's always going to be 101 kilopascals, always. It's always going to be that. It never changes. And the pressure of the unknown pressure, we found that to be 107,440. So the difference in pressure would just be the difference between those two. Understand?
yes, sir.
And let me show you something, right? So difference in pressure, delta just means change or difference, right? Difference in pressure, that would be 107,440 minus 101,000. Do that calculation from a fast and tell me what you get.
6,440.
6,440.
Mm-hmm.
Let me show you something, right? There's another way we could have calculated that. So pressure is equal to height by rho by gravity. What was the height difference?
30.
30. So
Millimeters.
that'll be 0.03. Check that for me. Just divide 30 millimeters by 1,000. 30 divided by 1,000, that'll be 0.003. Think
0.0.
yeah. The density of,
No, so it was correct.
I was correct.
Mm-hmm.
Okay. The density of mercury, we had it somewhere. It's 13,600. 13,600 multiply that by 10. When you work that out, you're supposed to get 6,440. You're supposed to. So 0.03. Let's work it out here. Right. So 0.3. Sometimes I just swear this virtual calculator battery die. Right? 0.03 multiplied by 13,600 multiplied by 10. That's a little weird. Why is that? Hmm. It's supposed to work out. Unless this calculation is wrong. Okay. I'm gonna check something real quick.
That's no problem.
Yeah, so I don't understand why we're not getting the same thing mathematically. It does check out. Like it does. It's weird. And you got it on your calculator.
No, so I didn't get the same thing.
Hmm. Yeah, that's weird. I'll look into that. I'll look into that. That's really, really freaky. Don't understand why that's the case.
Right.
Probably something that we're not considering because there's other pressures acting on it. All right. Let's look at hydraulic lifts now. So give this a read. By the way, do you know how hydraulics work? Like, it's a hydraulic press.
No, we didn't list it down.
You know it's a hydraulic press?
So we did not do pressure.
Okay, but you ever
But
seen
we
a hydraulic press before? Like on those YouTube shorts?
no. No.
You know those videos like where they would lower this thing and they would crush something. You know what?
I don't.
I don't think you know what I'm talking about. That's okay. All right.
Mm-hmm.
So give this a read for
The,
man.
di-
I'll explain the concept.
the diagram above illustrates an hydraulic press model demonstrating the relationship between the pressures of a plunge slash hmm,
Piston,
well
plunger.
piston,
Mm-hmm.
liquid, and ram. The plunger is pushed down with a pressure at P1. It exerts the same pressure in P2. This is denoted by Pascal's law, which states the pressure applied to a point in an compressible
Incompressible,
fluid
right?
is evenly distributed to all points in that fluid.
Right? Devices
Hmm.
following
Devices following the model act as force multipliers and can be used for lifting heavy objects by applying small amounts of force. This also explains why a force as small as a foot on a pedal could stop a moving car.
Yeah, you ever think about that? How a foot pedal could stop a car? You ever thought about that?
Not really.
Um, okay, is a car jack? Probably saying that wrong. I myself already know much about cars, right? You know the thing that they would place on the cars
Should I turn it up?
and then they would like press down on this and it would like they would put this under the car and it would push up and it would cause the car to rise. You know what I'm talking about?
Yeah.
Yeah, that's use hydraulics. So let me explain this. This is a really cool concept to understand. So, so stay with me, right? Shina, what's the formula for pressure? Just remind me. Want to go to
Force
a new
that
page.
area.
Add page after. Right. Pressure is equal to force over area, right?
Force that area.
Nice. I want to teach you this from scratch because it's a really, really cool thing to understand. I'm gonna find like a nice diagram. So I could just put on the diagram. Um, Let me just draw a diagram quickly. Okay, so Sheena, let's try to understand what's happening here, right? Let's try to understand what's happening. And I should tell you, anytime we're talking about area, we're specifically talking about the cross-sectional area. When we're dealing with pressure, we're talking about the cross-sectional area. Sheena, if I'm applying a pressure at this juncture, right? Pressure here. We could call this We could say that we're applying an input force, right? That's what we could say. So we could say that we're applying an input force over here, and we could call that force F1. Right. Now, Shina, as a result of me applying a force, wouldn't there be a pressure acting on the fluid? Because keep in mind, right, Shina, this entire thing is a fluid. The entire thing is a fluid.
Yes, sir.
Okay, Shina, if I apply a force to this what we call that again? Yeah, if we apply a force to the plunger, right? And by the way, this entire concoction here, this is a piston, right?
Okay.
Right? If I apply a force here, let me just make this a little more accurate. Yeah. If I apply a force over here and I push this down, what do you think is gonna happen to this one?
It will rise.
It will rise. It must rise. It has to. So my question is, the pressure felt on this side, wouldn't it be the same pressure felt on this side? Because if you're applying a force here, right, wouldn't there be a pressure acting down on the fluid?
Yes, sir.
Wouldn't that be the same pressure acting down on acting on this as well? Like
Yes,
over
sir.
here. It would be the same pressure, right? It'd be the exact same pressure. So what I'm trying to say is the pressure is going to remain the same. The pressure is going to remain the same. So you're going to have an input force and you're going to have an output force. You're going to have an output force. We call this F2. Now, if we want to calculate the initial pressure, P1, that's going to be equal to F1 all over A1. And Shina, the area for this would be the cross-sectional, right? Cross-sectional area. I drew it in 2D, but like I want you to imagine this being in a three-dimensional space, right? Like if it's in a three-dimensional space, it would look like that. And it would have a plunger here, pressing down on it. You can visualize that.
Yes, sir. Yeah.
Wouldn't it have an area over here? Like, wouldn't this have an area?
Yes, sir.
Right. So that's the area we are talking about. We are talking about the area for the three-dimensional square. Right. So P1 would be F1 over A1. Cool. And that would be the pressure felt on the fluid, right? With this given area. Okay, cool. Question. On this side here, for this piston, do you think it's gonna have the same cross-sectional area as the piston over here?
No, sir.
Mm-mm. That area, right? If you could think about it in three-dimensional space, it's going to be a lot larger, correct?
Yes, sir.
It's going to be a lot more, right? So P2 is going to be F2 all over A2. So let's go through a hypothetical. So you said that, so you told me, right? If I press down, if I press down on this plunger, right? Let's just say I press down this much on the plunger. And as such, I moved it this distance downwards, right? Say with me. Imagine you took that plunger and you applied a force to it, and it's now at this position.
Yes, sir.
Wouldn't it move it? By doing that, wouldn't it move a good distance downwards?
Mm-hmm.
Now, think logically, intuitively. This is a much larger, this is a much larger plunger, right? Do you think it's gonna move over by the same distance?
No.
No, it's not going to move over by the same distance. But we said at the start that the pressure needs to be conserved, right? The pressure must be the same.
Mm-hmm.
Yeah,
Yes, sir.
it must be the same. That's what we said. So I'll show you what's going to happen there. I'm not drawing this on top of this one because you wouldn't be able to see the blue one. So I'll just drawing a slight a little off center, right? Yeah. Maybe I should do it in a different color. Like like a light blue. I'll do that. Okay, so Shina, if the distance moved by the other plunger is less, and we know that the pressure needs to be conserved, and something strange going on there. Because I feel like at the start, you might have thought that, this would have had to move the same distance upwards, or you never thought that.
Not necessarily same distance.
You was never thinking it would have be the same distance, right?
Mm-mm.
Okay, good. What makes for pressure? Force on area, correct? So if this area is a lot larger and this area is a lot smaller, and so the area changing, right? The area is changing. We know that the area changing. So if the area changing, what will also change to keep the pressure the same? Think about it.
Mm.
Say that again.
Force?
Yeah, the force would have to change, right? The force would have to change. So tell me if you understand that.
Yes, sir.
Say with me so far, right? So
Mm-hmm.
initially you would have applied a downward force. You'd have applied a downward force, and that would have been the force acting up on these plungers over here, right? So let's do an example. What pressure do you want me to use? Give me a pressure.
How high?
Just give me a pressure. Like 100,000. Like in that range.
Within 100,000.
If you could say 100,000. So
Sure.
we know that P1 needs to be equal to, like, we know,
F1 over E1.
wait, Shayna, we are dealing with an incompressible fluid. Think about it. Can you compress air? Like, okay, let me explain what I'm talking about, right? Can you, like, if you had air trapped in a bottle, can you okay, with solids, you could press them. Like if you like, let me just say foil. If you had like a foil ball or something, if you press it, wouldn't the volume decrease?
Yes, sir.
Okay, can you decrease the volume of like air? Think about it. If you had a water bottle and the water bottle was filled with air, like let me give you an example. You ever buy like a liter Coke or something, and like it have real like the bottle really really stiff. You know what I'm talking about?
Mm-hmm.
Or just like a regular
Yes, sir.
bottle of Coke. Just a regular bottle of Coke. The bottle will be really really stiff, and
Yes, sir.
that's because it has a lot of gas inside of it. In case you didn't know, all gases are fluids, right? Do you
Mm-hmm.
think you'd be able to compress that? Like, you think you can compress that?
Yeah.
I don't think so. You can't compress air.
So the only reason is because in chemistry we learn that um gas could be easily compressed or expanded.
Okay, let me change it to a liquid, right? Let me change it to a liquid. Can you compress a liquid? Like, can you?
Yes, sir.
No, you can't, right? You can't. You can't compress a liquid. So remember at the start, we said that if you push down on this would have to rise because you can't you can't compress a liquid. You can't do that.
Yes, sir.
So if you apply a force here, it needs to rise over here. Great. So what I'm saying is the initial pressure is supposed to be equal to the final pressure. And we are saying that that's 100,000 pascals. Okay. What do you want the cross-sectional area for A1 to be? Give me an area.
Um, um, any area number.
Not too big though, like keep it between the range like 1 to 20.
Okay, 15.
And let me just say the area for A2 is let me just say 60 meters squared. All right. Say with me so far, right?
Yes, sir.
Cool. So here what we're going to do, right? We are going to use these numbers to figure out the force that would be felt at the input and the output. That's what we are going to do. Right? So Shayna, we are trying to figure out how much force we had to apply here, right? And the output force we'll feel. That's what we're trying to figure out. So P1 is equal to F1 all over A1. You agree?
Yes, sir.
Okay. If I made F1 the subject, what would that be equal to?
Force is equal to P1 times C1.
Okay. What's P1?
100,000 pascals.
That's what would you end up with? Oh, I shouldn't.
Oh, sorry. 1,000, 1,500,000.
Say that again.
1,500,000. So
1,000.
1,500,000.
Then that would be, I think you say that wrong. That'd be 15, right? 0, 0,
Mm-hmm.
0, 0, 0.
Mm-hmm.
So that'll be 100. No, that'll be 1,500,000.
Oh, right.
Yeah, that'll be 1,500,000. Right? And that'll be newtons. Okay. We know that, like, let's just look at P2 side, right? P2 will be equal to F2 all over A2. So we know that the pressure needs to be the same, right? Pressure needs to be the same. So it'll be 100,000, and that's going to be equal to F2 over A2. Let me just make F the subject of the formula one time. If we do that, F2 is going to be equal to P2A2. What's your pressure?
100,000.
Right? Pressure is 100,000, and we're going to multiply that by the 60. And if I do that, I should get 6, 0, 1, 2, 1, 2, 3. So that's how much? That's 6 what? What's that one? 6,000, eh?
6 million.
6 million, right? 6 million what?
Yes, sir.
Okay. So Shina, let's try to understand what's happening there. So you understand the part where I say the pressures need to be the same because it's an incompressible fluid.
Yes, sir.
Okay, great. So I said P1 is equal to P2. Now, P1 would be equal to F1 over A1, and P2 would be equal to F2 over A2. We understand that. Now,
Yes, sir.
you also understand that if I apply a force here and I push this down, this would have to move up, right? You understand that?
Yes, sir.
Now, I'm keeping the pressures the same. I'm keeping the pressures the same, but we're noticing a little discrepancy. If we push this down with a distance d1, then the other piston is not going to move up by the same amount. So we need to account for this. So how are we going to account for this? By doing this. So you'll see where I'm going with this. So P1 is equal to F1 over A1. So F1 will be equal to P1 A1. So we found that the force, the input force, was 1,500,000 newtons. Now, P1 and P2 need to be the same. So when we find for F2 using 100,000 pascals, we got 6 million newtons. Shana, are those numbers the same?
No, sir.
No, they are not the same. They are not the same by any means. So let's try to make sense of that. Let's try to make sense of that, right? Do you remember the formula for work? Tell me, Shana, do you remember the formula for work done?
Um, Force by distance.
Force by distance. Can we both agree that work done is energy?
Yes, sir.
Yeah. Could energy be created or destroyed?
No, sir.
No. So if I supply energy to push this down, wouldn't that need to be the same amount of energy that's pushing that up?
Yes, sir.
Okay. So stay with me, right? So we know that work done or energy, right, is equal to F by D. We know that. And we also know that energy or work done needs to be the same throughout. So look at what's going to happen. I'm essentially saying that W1 needs to be equal to W2. So I'm saying the work done on this piston needs to be the same amount of work done on that piston. The same amount of work.
So I think let's say a real breakup right now.
I'm breaking up plenty. All right, let me know if you're hearing me. Are you hearing me any better? Shida? Sound check 1 1. Are you guys hearing me?
Yes, sir.
Yes,
So
sir.
maybe because somebody else joined my Wi-Fi, we had to trip off, but I don't know.
Let's say that again.
Honestly, maybe because somebody else joined my Wi-Fi, decided to trip off. I don't know.
Oh, yeah, enjoy on your Wi-Fi. Start to play up.
I join a good 15 minutes now. Don't try that. And you was breaking up for me as well, sir. So yeah.
Well,
So let me continue, right? So Shina, do you understand that the amount of energy I input into the system needs to be conserved?
yes, sir.
Okay, so W1 needs to be equal to W2. If W is equal to F by D, NW1 would just be F1 by D1.
Yes, sir.
And what would W2 be?
F2 by D2.
Are the forces felt on the pistons the same?
No, sir.
They're not the same, but we know that the work done needs to be
The same?
exactly. The work done needs to be the same. You can't create energy, right? Whatever energy input needs to be the output. So let's see what's going to happen here. So if W1 is equal to W2, we could come up with this equation. We could say that F1D1 is equal to F2D2. So Shayna, the whole question now is, how are we going to prove what we theorized over here? Because remember, we said that if you push this, if you apply a force, it would move a certain distance, and the distance here would be more than the distance over here. And we said that, and we gonna see it happening.
Yes, sir.
But now we need to actually prove it. So let's prove it. Which distance you want to find for first? D1 or D2?
D1.
Okay. Um, to do that, I would need to tell you. I would need to tell you one of the distances. So
Yes, sir.
let me just say that this distance over here is 50 millimeters. Nah, that's too little bit. What about like 30 centimeters? All right, 30 centimeters. So I'm telling you that D1 is 30 centimeters. So Shayna, if our calculation and what we came up with is correct, right? Should D2 be less than 30 or should it be more than 30?
Yes.
It should be less. We should see that it's less. Right. So Shayna, if I want to find the D2, I would need to make D2 the subject of the formula, and D2 would be what?
You will divide on both sides by F2.
Correct. So that's
So
going
it
to
will
be
be F1 by F1 over F2.
great. What was F1? Oh, Shayna. Oh, Shayna, I'm not hearing you. Jayla, am I breaking up plenty on your end? Or are you hearing me?
I'm sorry, so yep,
I mean,
sorry.
yeah, I think she probably dropped. I don't know.
Oh, Shayna, you hearing me?
So I know, yes.
Okay. So Shayna, we're trying to find for D2, right? Given D1. So what's F1?
1,500,000.
So 1,500,000. What was D1?
To T. Well,
You to convert
0.1
this,
meters.
right? So that'll be 0.3, right? Right. Just confirm that. Yeah, it'll be 0.
Okay.
And that would be over F2. What was F2?
6 million.
So you should see that 1,500,000 over 6 million is a quarter. Just confirm that though. Confirm that. So 15 million, no, so that's 1,500,000 over 6 million. That should be a quarter. Should be. Because if I cancel off all of these zeros,
Yes, sir.
right, you get 15 over 60, which is a quarter. So that will be a quarter of 0.3. And what's a quarter of 0.3? You should get 0.075 meters.
Yes, sir.
Right, so Sheena, was our theory correct?
Yes, sir.
Okay, it was correct. Now, Sheena, why would this be useful in real life? Let me think. Why would this be useful in real life? So you notice that, let's just go through the findings, right? You notice that the distance here, the distance it moved here was a lot more than the distance moved here. You're seeing that, right? It was a lot more.
Yes, sir.
But what was the input force? Just remind me, according to what we found, what was the input force?
Man, gonna be checking it over.
Right. And what was the force felt at the output?
6 million.
But it moved a small distance, and
Mm-hmm.
why would that be useful?
Um,
Shana, what's happening to the force? What's happening to the force? It's being, starts with M. The force is being what?
say it was that.
That's with M. MU. MUL.
Multiplied. I wasn't expecting it to be multiplied.
Yeah, the forces are being multiplied by the ratio of the area. Because watch, if you compare the area, right, wouldn't it be 15? Okay, 60 over 15, right? 60 over 15 is 4. And the force is being multiplied by that ratio. Watch. What is
Yes,
1,500,000 by 4?
6 million.
Right. So Shayna, how would this be useful? Let me think. In what situation would me multiplying a force be useful? Like, I'll help you, right? In a garage. Think of a garage. Why why would I want to use this property? So this property here is, if you apply a small force, you could get a much stronger force. Why would that be useful?
I don't know. So,
So Shayna,
I understand the concept. It's just the everyday application.
okay. So Shayna, this concept here is saying that if you apply a large, what am I saying large? If you're applying a small input force, right, the output will be multiplied. So you put in a small force and you get a weaker or stronger force.
Sure, so yeah, sure, and
Right.
yes, understand concept is just the example.
All right, so you're getting a stronger force. In what scenario would you want to, to amplify your strength? I'll put it like that. Like, give my example with a car. Like, let me just say you're fixing a car, right? If you want to work under the car, obviously you need to what?
That's it.
Mm-hmm. You feel like you have enough strength to lift a car?
No, so
No. So Enchi would want to find some mechanism where you could like put a weak force and get a much stronger force out.
mm-hmm.
Yeah, that's where this comes into play. That's where this comes into play. So Jaden, and you know it's like a lifting jack, like the thing where that's look like this, and you press down on it and it is
Yeah,
bigger.
it is like send up like a little piece that is push up the car.
Exactly. we actually covered the mechanism by which that works today. This is how it works.
Mm.
It works on hydraulics. So what happened, right, Jadon? And you would apply a force here, and this would move a lot, but the thing inside here would move a little bit.
Yeah.
Okay, but and the force at this point would be a lot more than the force that you putting in.
Yes, it would.
Yeah, because we you think you could lift up our entire car?
Yeah, but realistically speaking, no.
Realistically speaking, no. I like that. Yeah, you can't do that. So and it would be nice if it had some mechanism where you could put in a weak force and get like a much greater force.
Yeah,
Yeah, so that's what we discussed over here.
like a pulley system, and that's also a good reference.
Yeah,
But yeah.
right. This is a hydraulic system.
Hmm.
So Jalen, how this works, right, is that you would you would apply an input force, right? And this input force would push the incompressible fluid. So I'm gonna run through the concept one more time, but Shana, you could see how this principle works in this application.
Yes, sir.
Because Shana, when you after class, right? I hear it myself. Like I really hear it myself. Jidon, see if you could mute it.
Oh, I,
Yeah, Shana, unmute on. Let me see if I still hear it myself. Sound check 1 1. Okay, and I hear it myself. That's good.
Okay.
Shana, after class, ask your dad um to s- to in like you could ask him to set it up for you, and like you could press on this and you would see a small thing over here. It'd be going up.
Okay, sir.
So what would happen, right, Shana, is you would press down on this and you would move this a relatively large distance, right? You would move it a
Mhm.
large distance, and you would have something inside pushing up, but it would be pushing up at very, very small increments. So you like real you real pushing down on this and it moving a great distance, but this is only going to
Mhm.
move a small distance. But by it moving a small distance, what is multiplied?
The force.
The force, yes. So you are putting in a weak force, right? But you're getting in, but you'll get but at the output, you're getting a much larger force, right?
Yes.
Yeah. So I think you understand it. So that's good. And this is an example. Right? So Jidan, I'm going to explain this here, right? It's gonna get a quick refresher on it. Let me see if I could just find a picture of the car jack. Okay, nice. I get a picture here. Cool. All right, so Sheena, I'll show you see this before, right? And you see this before?
Yes, sir.
Okay, good. And let's look at a use case of it, like it actually being used. All right, so Sheena, look at this guy. All right, look at what he doing. Wouldn't he have to push this down all the way here?
Yes, sir.
Yeah, he would have to. So he's moving the handle a great distance. You see this thing over here? You see that,
Yes,
right?
sir. Mhm.
Every single time you move this a great distance, this is going to move, but a very small distance upwards. But the force is going to be a lot more than the input force. And that's what's allowing you to lift the car. Everything make 100% sense for you, like no
Yes,
confusion.
sir. No confusion.
Okay, good. All right. So you're done. Let me explain that back for you like in 5 minutes.
hmm
So Jadon, you need to know that pressure is equal to force over area. You need to know that. That's the formula we're going to use. We are saying that, let me just fix up this diagram so that it will make more sense for you. So you see the dark blue? That's the initial position. Initial position. That's how it was. That's how it looked initially. So initial position. Right? And the light blue is the final position. All right. Okay. Jadon, you there?
Yeah.
All right. So Jadon, what going on here, right, is that you see these things? Those things are plungers. Right? You just think of it. I think this was a nicer diagram over here. Yeah, this is a 3D diagram, right? So this is what you really have, right? So you have a plunger over here, and this is a ram, and these two things together, they form a piston. Understand? Tell me if you understand that.
Yes.
Okay. So what you're seeing here, so right, so this will be the plunger, and this will be the piston. Yeah? Like the entire thing will be the piston, right? So this is the plunger, this is the ram, and this is the piston. The entire thing is the piston.
Mm-hmm.
This is the piston. You sure you understand that?
Yes.
So, Jidan, if you apply a force to the ram, wouldn't you push the piston downwards to this position now?
Yeah.
Yeah, so all you're doing is, watch, you're applying a force. If you push down, we say now you're reaching that position. So that makes sense for you, right?
Yeah.
Great. So the light blue is the final position. So it reaching over here now. Now, Jaden, do you think you could compress liquids? Do you think it's possible to compress a liquid like water?
Oh, no.
No. If you have a bottle of water, you feel like you could decrease the volume of that?
Nope.
No, you can't. So here what's happening, right? If this and this is the initial positions of the plunger, right? And we're saying that inside it have some incompressible liquid or fluid.
Yeah.
When you push over here, what's gonna happen to this dark blue plunger? Is it
It's
gonna
gonna
stay?
rise.
It's gonna rise. That makes sense. It's gonna rise. Now the question is it going to move the same distance that you pushed it down, or is it gonna move a lesser distance? What do you think?
Um, I'd say a lesser distance.
I would say a lesser distance as well. Because when you think about the cross-sectional area, right? I mean, it's kind of hard to see here, but if you look at it in three-dimensional space, you would have your plunger inside here, and it would be pushing down. So,
Mm-hmm.
where do you think the area is greater? Do you think the area is greater for this side or this side?
The next side will.
This side, right?
Yeah.
Because of the large area, right? This is not gonna move the same amount of distance. Understand?
Mm-hmm.
It's gonna move like a lesser distance. But in doing that, the force is going to be a lot more. So let's try to understand the theory. So Jadon, you understand that you can't compress a fluid. So if you apply a pressure on one side of the fluid, the pressure at the other side needs to be the same.
Yes.
Okay, so we're saying that P1, the pressure at this side, is equal to the pressure at this side. That's what I'm saying. So P1 is equal to P2. We know that P1 would be equal to F1 over A1. So F1 would be the input force, and A1 would be the area for that piston. You understand?
Yeah.
Okay. So F1, if I make F1 the subject, I would have to multiply both sides by A1. So F1 would be equal to P1 A1. So P1, we said, this is an example, right? I said that P1 is 100,000, so that'll be 100,000. And I said that the area was 15. This is an example, right? So we got F1 to be 1,500,000. Say with me so far.
Yeah.
So we just agreed that the area for the area for this piston would be less than the area for this piston, yeah?
Yes.
So if I give you A2, obviously A2 has to be more. So this I just given you a scenario over here. So I'm telling you that the area for this one is 15 and the area for this one is 60. So the area for this one is 4 times, right? So 4 times the area. Right. So I didn't lose it or anything, right?
Nope.
Okay. Let's find for P2 now. So P2 is equal to F2 over A2. And again, Jaden, I said that since it's an incompressible fluid, the pressure on one side needs to be equal to the pressure on the
Other side.
right. So P1 needs to be equal to P2. So if I said P1 is 100,000, P2 also has to be 100,000. So I know that P2 is going to be 100,000. Great. Now, how would I find for F2? To find for F2, I would multiply both sides by A2. And if I do that, F2 is going to be P2 by A2. So Jadon, what we're trying to find for here is the force that would be felt on the other plunger. So Jadon, you understand that, if you apply a force here, the other plunger would experience an upward force. That makes sense?
Yes. Yeah, that makes sense.
So we're trying to figure out what that force is, the output force. So F2 is equal to P2 by A2. Now, we said that the pressures will be the same, so it's 100,000. And we said that the area will be more, so we say 60. So what you notice about the output force? The output force is what? Less than the input or more than the input?
Less.
Do you find so?
Oh, we don't know. Yeah, we're not watching it.
Where's the output force?
6
Call out.
million.
Okay, and where's the input force?
Oh, 1.5 mil.
Exactly. So tell me, the input force is more than the output force? Or is it less than the output force?
You're gonna think up again. The output force is greater.
I'm saying back one more time.
Yeah.
Say back one more time.
Mhm.
Is the input force more than the output force?
No.
No, it is not. So Jadon, this is really cool, right? Because we applied a lesser force and we got a
Greater.
right. Doesn't that ring a bell?
Yes, it does.
Right, does ring a bell. So we understand that part, right? Now we need to justify the distances. So let me show you how we're going to do that. So work done, which is energy, is given by force by distance. That's what work done is. Now, Jaden, from the last couple of classes, I would have said that your energy can either be created, no? Let's see if you remember. Energy can either be created, no.
I can't remember.
Okay. It can either be created nor destroyed. So
Okay.
you can't just magically create energy. If you applying a certain amount of energy over here to move this piston, and that same amount of energy needs to be conserved.
Mm-hmm.
You understand what I'm saying? Because again, it's an incompressible fluid. So if you're applying work on it, then the work at the output needs to be the same amount of work you're applying. The work needs to be the same, right? Jadon, if you try to understand what I'm saying you can't just magically create energy. If you if you're inputting a certain amount of energy at the output, you need to be getting the same amount of energy or less. Why I say less? Because you could lose energy in the process. It could be converted to other, like heat or something, or it could be lost via friction.
Mm-hmm.
But I get what I'm saying, right? You understand what I'm saying?
Yeah.
So
Yeah.
question: if I put in 500 joules of energy into this, can I expect 600 joules at the output?
You put in.
If I put in 500
Yes. You
joules of
could.
energy, no, I can't.
But and if you put in, and this is the whole point of putting in more, putting in less energy into the first side,
Nah,
you're
nah.
gonna get
Energy. It's not energy, it's force.
more
I will show you
force.
something. I will show you something. Energy and force is not the same. I
Oh,
understand why you're confused. You're thinking, well, you know, well, I I apply in a weak force and again a greater force, right? So that means it amplifying my energy. That way you're thinking, it?
yeah, sort of.
Yeah, but that's not the case. That's not the case. Energy is still being conserved. So watch. If I apply 500 joules of energy, then I need to be outputting 500 joules of energy as well. I can't just magically create energy. So Jadon, you must be thinking, well, if it's if I'm not creating more energy, then it must have a drawback, and
Mm-hmm.
okay, this is the drawback. Watch. And he have to move this thing a great distance for this just to move up by a little bit.
Yeah.
That's the drawback. Let us soak in. So and this man would have to push this like push it up and down like a good amount of times for this to go up by a little bit.
Yes, he would.
Yeah, isn't that a drawback?
It is.
So is he really creating energy or is he just putting in a lot of energy into the system?
He's just putting in a lot.
Exactly. For this to go up by a little bit. Yeah. That's what happening, right? You understand?
Mhm. Okay, yeah.
Okay. And now we're gonna prove that. So I'm saying work is equal to force by distance. And Jadon, like we just now disproved, if you put in 500, you can't get 600, right? You understand? If you put in 500 joules of energy, you cannot get 600 joules out. You need to get the same amount out, right?
Mm-hmm.
Right. If I put in 1,000 joules over here at the input, how much joules I would get at the output?
1,000.
Exactly. And where's the trade-off? Again, more force, but what happened into the distance?
It's going up. Well, it's way less. Like the distance is just less.
Exactly, right? So that's the
Mm-hmm.
trade. So W1 is equal to F1 by D1. And W2 is equal to F2 by D2. So I'm saying the work at 1 is equal to force by 1 by distance by 1. And the work at 2 is equal to the second force by the second distance. You understand what I'm saying so far? Or like I lost you.
I understand.
All right. So you understand that F1 would be the input force and D1 would just be the distance in which it moved.
Yes.
And do you understand that at the output, F2 will be the force I feel lifting it up, and D2 will be the distance it moved. You understand that?
Yes.
Okay. So now I can say F1 D1 is equal to F2 D2. Why? Because Jadon, any work done needs to be the same.
Yes.
Right. It needs to be the same. So that's how I could put this on this equal to each other. Now, I told you that D1 is equal to 30. So we want to find for D2. So to find for D2, I'll divide by F2 on both sides. So D2 is equal to F1 D1 all over F2. So, Jadon, we found out F1 was 1,500,000, so I put that in there. I told you that the distance it moved at the input side was 30 centimeters, which is 0.3 meters. You need to use meters, you can't use centimeters. And what was the output force? What was the force felt at the output?
6 million.
Right. So when you work this out, you're gonna get a quarter of the 30 centimeters, which is 0.3 meters. See, you're seeing that the distance moved at the output is 0.075 meters. Seeing that?
Yes.
Yeah. And how much did it move initially?
How much it move? Wait, for the
At the input side.
you mean in D1, right?
Yeah, D1.
About 30 centimeters.
Let me convert that 0.075 to centimeters so you go kind of understand it a little better.
Mhm.
So this is 7.5 centimeters. And that's D2. So Jadon, you understand that you'll put in a weak force, you'll get a greater force. But you'll have to do a lot of work to get the distance to be what you want it to be. Because the trade-off is that the output is going to move a little bit. The distance is going to be less than the input. That makes sense?
Yeah.
Right? So Jadon, let's just discuss the trade-offs, right? So let's just write down a couple of facts though, right? So a couple of facts we need to write down. So P1 is equal to P2. You cannot compress Jadon, I would say that the output force is what? The output force is
The output force is lesser.
no.
How is this not lesser? Isn't the output force referring to the okay, greater.
Right, the output. Remember, the output is the force you're getting at, like in this case, right? This will be the input. This will be the input section, and this will
Mm-hmm.
be the output section.
Okay.
Is
Yeah,
the
right.
force? Yeah, yeah. I think you understand that. So the
I
output,
understand. I just keep mixing it up. I understand those.
so the output force needs to be more than the input force. That's what will happen. What about D2? D2 will be what? If you're comparing D2 and D1, D2 will be what? Tell me, Jadon, what D2 be?
Is the distance. So that is the distance of the second. Well, I guess
The second plunger.
the plunger, yeah.
So the distance moved by the second plunger would be more or less than D1. You tell me.
The distance would be less.
Yeah, it'll be a lot less, right? So these are the general facts I need to know. Yeah. Right. So you feel like you understand it?
Yeah.
Okay, good. And if we look at this example over here, we could see that this would be D1, right? And I would call this the input side. This would be the input side. And well, he's applying a force. Right? And over here is the output side. Right? Right. So Jada, like it make perfect sense for you. Like,
Yeah.
okay, good. Glad to hear nobody is confused. That's great. Right. Shina, this easy now, right? Can I hear Shina? Do I assume that it's hard?
No. My mic was just thinking.
So you
So you
find
get me?
yeah, hearing you.
Okay.
So you okay with everything we did here, right?
Yes, sir.
All right. You understand the summary that P1 is equal to P2, you cannot compress a fluid. So and W1 is equal to W2. The output force is more than the input force, and the distance moved by the second plunger is less than the distance moved by the first plunger.
Yes, sir.
Great. Great. So, right, and this is what we have here. So this is essentially what we just covered, right? That's what we just covered. Right? So the diagram above illustrates a hydraulic press model demonstrating a relationship between the pressures of a plunger, piston, liquid, and ram. When the plunger is pushed down with a pressure at P1, it exerts the same pressure in P2. Right? And this is denoted by Pascal's law, which states that the pressure applied to a point in an incompressible fluid is evenly distributed to all points in that fluid. You need to know this. This is very important. Pascal's law. It is essentially the fancy way of saying what we just said, right? So so Jalen, and logically, and you can't compress our liquid.
Yeah.
Yeah, well, this is the fancy language I had to use. You had to say Pascal's law. You had to tell them that in the exam. You had to say because of Pascal's law, which states that a fluid can't be compressed. Yeah. Right.
I remember them saying like, well, not them. One of my friends who wrote physics, he said, "Oh, you have to memorize all the laws and stuff because they would ask you it in exams." I mean,
Mhm. Yeah, you need to remember aggregate formulas and aggregate laws.
how much laws are there?
I can't tell it off the top of my head, you know. But I think at this level you need to know like 10. I had um I had sent you all a summary of everything that you needed to know.
Yeah, the video. Not the video, the folder, I believe.
This thing.
Mm-hmm. I
So
kind of went through that.
Newton's first law, Newton's second law, Newton's third law, law of conservation of linear momentum. You need to know about Archimedes' principle of moment, Hooke's law, law of conservation of energy, Pascal's law, Boyle's law, Charles' law, pressure law. I think I mentioned Hooke's law, yeah. You need to know Hooke's law. Mm. These aren't laws, but you need to know them. You need to know the definition. Specific heat capacity, latent heat of fusion, specific latent heat of vaporization, kinetic theory of matter, two laws of reflection, two laws of refraction, refractive index. You need to know Faraday's law, Fleming's left-hand rule, Ohm's law. You need to know all of those laws. Does it sound overwhelming?
No, not too much.
Not too much.
I just say no because it's like, I guess in this sense, it's just a matter of like reading and learning them over.
And you see, like a lot of them is like common sense, you don't find? Like the incompressible fluid part. Like if you forget an exam, I feel like you could come up with that. Hence,
Yeah.
no, because like think about it again, you can't really compress a liquid. You can't, if you have a bottle of water, you can't compress that. You can't decrease the volume, right? you just simply can't compress fluids. You can't do that. All right. Yeah. Right. All right. So let me see if I give all that question. Okay. Right. So Jaden and Sheena, I'd like you to try the example question.
Yes, sir. I'll try this time. And honestly, yesterday on work, I was trying to tackle the question, and it
This
was correct. I kind of lost myself,
oh
and yeah,
that's a question, you know. That's not the homework question.
remember. No, but I'm just talking about the homework now.
Oh, this wasn't the homework, but the homework was giving you a little bit of trouble.
Sort of. You know, so it's like I was just like I was doing it whilst on work, so I can to kind of battle tackle both of them at the same time. It wasn't ideal. I'm not that good at multitasking, so yeah.
Not to worry. It's the same thing with me. I can't multitask. It's for nothing. I really can't. But you go look back at the recording and the solutions, and if you're still confused, you could always reach out to me.
Yeah.
All right. All right. So you all could go ahead and try this question. Right. If you want, you could probably take a screenshot of this or something. Take a screenshot of that. All right. I give you only 5 minutes to try that question out. So Shayna, did you notice a trend? Any trends you notice?
Um, right?
Let me get a little let me get you in the correct way, right? So you notice that the output force was how much times the input force.
4 times.
You notice that the area of piston one was what
Four
fraction?
times. Mhm.
It was a quarter of the area of piston two, right?
Mhm.
So like you see that pattern, see that trend here.
Yes.
Yeah, so the force is directly proportional to the ratio between the second area and the first area. So just by looking at this question, right? It looked like the force over here is going to be how much times the force over here? Tell me, Shina. The area over here.
Five.
How much was the area over here?
2.
How was the area over here?
10. So 5 times.
Yep, 5 times. So
Okay.
you can already figure out part three then. What's the answer for part three? Tell me, Shina, what's the answer for part three? So you know how much times it'd be greater. Just had to multiply now.
Oh, right. Okay, so well done. Alternative weekend.
You're done with everything? One, two, and three?
Uh-huh.
Okay, nice. Sweater. All right. So Jaden are going to do working, right? These questions easier than they seem. Right. So Jaden, read part one for me.
Um, Calculate the pressure exerted on the liquid by the small piston.
Okay. And what did they give us in the question?
They gave us the Well, the force is the force. If a 20 Newton, no, hold on,
You see,
Newton's force is applied to the piston,
right,
and then give the distance of the first piston and the second piston.
correct. So let me just do a couple labeling, right? Do some labeling here. So the force on this, I would call that F1, correct?
Mm-hmm.
And I would call this distance D1. And if I'm pushing down on this plunger, yeah,
Yeah,
would this plunger be pushed down or would it be pushed up?
it'll be pushed up.
With a greater distance or lesser distance?
Less so.
Perfect. You have it, you have it. And the force, we know the force is going to be a lot more. So I should probably just let me just bro. Let me just make this this a little shorter here. All right, so this is F1 and this will be F2. Notice the terminal line is longer. And Jaden, I'm doing that to kind of show that, this force needs to be less than this force. Remember, the force at the output is going to be more. So you want to draw the line longer than this line. Understand?
Yeah,
Right? This is going to be D2, right? And this part over here is going to be A what? What's that going to be?
that's gonna be A1.
No, A2. Right? This is going to be, wait, this is not D1, eh? This is A1. D1 would be the distance moved. I don't think they ask us that. That's a good opportunity for me to add in a new question. Yay. Right. So Jalen, we label everything. Great. Part one, calculate the pressure exerted on the liquid by the small piston. So Jalen, what's the formula for pressure? Pressure is equal to what over what?
Pressure is equals to, that's not, I have it. Are you talking about the P2 formula or the P1? Where is P2 equals to F2 over A2?
Okay, wait. Both of them formulas is the same thing. Right? It's the exact same thing. The reason why I said P1 and P2 is because it was one was for the first pressure, one was for the second pressure. So Jalen, if we are talking about the pressure for the small piston, do you think that's P1 or P2?
Pressure, that's P1.
Right, so I'll say P1 is equal to F1 all over.
F1 all over A1.
Right. What's the force I applied to the plunger?
20 newtons.
Right. What is the area of the piston?
10 meters squared.
No, the small piston.
Very small, 2 meters squared.
Because it said the small piston.
Yeah.
So what's the pressure?
It would be 10
What's the unit for pressure?
newtons.
Nope.
Oh, PA,
Right, pascals, PA.
pascals, yes.
Right, part two. Determine the pressure on the large piston. So they want us to find what then? That'll be what?
Determine any pressure on the large piston, so they want that'll be the I guess the force that is pushing up the piston.
No, they want the pressure. Pressure. It's very similar to the first question, because in the first question, we calculated the pressure on the small piston. Matter of fact, we don't have to do any working. I know you could figure this out, Jalen.
I don't have to do any working.
You don't have to do any working.
Determine the pressure on the large piston.
But if you did have to do working, though, what formula you'd I use?
Mm,
Okay, you'd I use P2, because they're asking you for pressure. P pressure, right? If you did have to use our formula, you'd I say P2 is equal to F2 over A2. Right? Because P stands for pressure, so you'd I use the pressure formula. But you don't have to do that. And the reason for that is because inside here, you have an incompressible fluid. So if I apply a pressure here, that pressure will be the same pressure on this piston. It'd be the exact same pressure. So P1 will be equal to P2. And what's the law for that? Do you remember?
no.
All right. That's okay. Read Pascal's law for me.
The pressure applied to a point in an incompressible fluid is evenly distributed to all points in that fluid.
Right. So that's what we're using. Right? So the pressure applied to a point in an incompressible fluid is the same at every point. So the reason why we can see this is because of Pascal's law. Pascal's law. And do you remember what Pascal's law said?
The pressure that is applied, is something I just read?
Yeah, the same thing I just read.
Pressure that is applied to an incompressible fluid is something.
Is the same at every point. Right, Jalen, you understand that?
Yeah.
All right, so if P1 is equal to P2, what would P2 be equal to?
The formula for P2 is,
Nah, you don't have to use the formula. Don't have to use the formula. We saying that P1 is equal to P2.
oh, is the same. So
Mm-hmm.
it'd be 10 pascals.
Yep, it would be 10 pascals. It would be 10 pascals. It's not changing.
Okay.
All right. It's the same pressure, right? And the reason for that is because it's an incompressible fluid. You can't compress it. If you apply a pressure at one point, it'll be the same pressure at another point because you can't compress it. Understand?
Yes.
Okay. Part 3 now. Calculate the force, right? Calculate the force exerted by the large piston on the load. So, Shina, want to help me with part 3?
Okay.
Right. Yeah, so tell me. So if I want to find for force, what formula
Like,
comes to
you
mind?
want to do some more? Yeah, well, you could use pressure equals force over area, and you rearrange your formula to be force equals pressure times area.
Correct. And since we're dealing with a large piston, should I use A1 or A2?
A2.
A2, right? So I'm gonna write the pressure in terms of that. So I'll say P2 is equal to F2 all over A2. And I'll need to make F2 the subject, right? Because they want us to figure out the force. So to make F2 the subject of the formula, I'll have to multiply both sides by A2. And if I do that, I'll get P2, A2 is equal to F2, and then I could just switch around. So F2 would be equal to P2, A2. Okay, done. Would you have had known how to use that formula? Be honest with me.
The P2 equals to F2 A1. F2 over A2, sorry.
Yeah, for part 3.
Honestly, no, because I was thinking I'd had to use it for part 2.
I know it's kind of tricky, right? Kind of tricky, but remember, you can't compress a fluid. So if you apply a pressure at one point, it will be the same pressure at another point. So P1 is equal to P2, no work in there, right? In part 3, though, they want us to find the force exerted by the large piston. So, Jadon, if we're dealing with the large piston, right, then the only formula that we have for the large piston would be P2 is equal to F2 over A2. That, remember that?
Yeah.
Right. Okay, cool. By multiplying both sides by A2, so I multiply both sides by A2, the A2 there and the A2 there would cancel off. So that would leave me with P2, A2 is equal to F2. And so now I could just switch the left-hand side and the right-hand side, and I would get a F2 is P2, A2. That's it. Right?
Mm-hmm.
So Jadon, what is the second pressure?
What is the second pressure?
Yeah. What is the pressure on the large piston?
I feel like you're trying to trick me.
No, I'm not trying
Because
to be like I'm not.
won't it be the 10 pascals that we calculated in part 2?
We didn't even calculate that, to be honest.
Well, yeah, well,
Right?
okay.
But yes, that is it. 10. That's the 10. Right?
Mm-hmm.
Okay. And what's E2?
A2 would be 10 meters squared.
Right. Where's 10 by 10?
1,000.
Nah, 10 by 10 is 100.
I'm sorry, yeah.
I wish 10 by 10 was 1,000. That we had I have real money in my bank. Right? 10 by 10 is 100. And where's the units for force?
The unit for forces, no, we're fully gonna die. Pressure is PA. Force.
Force have a fixed.
Will it not? It have a fixed.
Yeah, like force always has like a fixed unit. I'll give you a hint. Isaac what? Isaac,
Newton.
yes. Right? Force is always measured in newtons. Right? Force is in newtons.
Mass, newtons, force, distance, acceleration,
You need to know all of those units.
initial velocity, time, final velocity. I'll have to go back to my maths days and have like a book, a mini book dedicated to just the formulas and
Units.
mhm.
I could recommend doing that. Should do that. Make sure you
Yeah,
know.
I did that for maths. It helped, not gonna lie. I'll have to do it again though.
All right. Yeah, honestly, you should start back. Because you had to know these formulas and you had to know these units, right?
Hmm.
So Shayna, if you look at this question, that's another way to answer part three would have been to look at the ratio between A2 and A1 and just multiply that by the force applied to P1. I want to say in
Yes,
P1. The force applied to the first plunger. So,
yes, sir.
so another way to work this one out would have been to say, or F2 is just equal to A2 all over A1 multiplied by F1. That's another way you could do it. That would have been 10 all over 2 by 20. That would have been 100 newtons. Great. So I'm adding another question. Because why not? Why not? If okay, if D1 was 50 centimeters, calculate D2. Right? So guys, try that question. Try part 4. Okay, I want you all to be able to see all the information. Let me just share this thing up then. Right. I believe you could see everything on the screen there.
If D was 50.
Hmm? Wait, Shana again, sure.
Started this thing. I can now come back, but yeah, I started.
Okay. Right, so we want to figure out what D1. Okay, if D1 was 50, what would D2 be? And another way to do this is also the ratio. But I'm interested in seeing what they're gonna come up with. All right, Shina, you have an answer? Okay, Shina on here. Wi-Fi connection. Jalen, you have ideas to what to do in part four.
I kind of watching over the formula and mix and matching. Not mix and matching, but like drawing references, I guess. So
So what formula has D in it?
I was seeing the one where it was like F1 and D1 equals to F2 and D2.
Yes.
And it was D2 equals to F1 over D1 over F2.
Yep. That's self. That's self.
Yeah.
That's it. Also, next class, we're going to start thermodynamics, which is the study of heat. It's a pretty intense topic. We are a good way into the syllabus. That's great. Like halfway into the syllabus, if not a little more than halfway into it.
So F1 would be um the 20 newtons.
Correct?
Okay. All right. Mm-hmm. You cooking with gas.
Yeah, we cooking with Ramco gas to be specific.
Mm. 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 15, 50, and all of that F2, which was 100, 29. Oh my, the Lord knows how much I want to catch and cook that chicken. I don't even eat chicken, so but that chicken has pissed me off.
You're unmuted, eh? We could hear you talking about the chicken.
Nah, it's good. It's good. So when I do cook the chicken, you will get chicken
I hope I will get
because
I hope I'll get chicken breast. I hope so.
that chicken real annoying, no. That you know what that chicken is do? I have well, not I, my neighbor has this hedge wall. She has a big wall, and she has cherry trees and everything, and it just grow vines all over the wall. And then the chickens just climb it, stand up right there, which is right next to my window. And at the crack of dawn or in the middle of the night, you just hear them going off.
They had to make a new song because in the middle of the night. Yeah,
That is so annoying. Okay, so I get 10.
you get 10. Oh,
Mm,
send me a weekend. Let me see what you do.
mm, that's not I don't like that. You get 10, it making my song on show. Your man's like, hold on. Trying to watch and see why. I was trying to reference to what you did. You cancel out this. Huh. Will you get 1/4?
1.5 million divided by 6 million is a quarter.
Okay, well, all right. You cannot. You confuse me when you cross all these zeros, not gonna lie. If you do that.
Well, if you multiply any zeros, you cancel off. But this zero can cancel off, eh? A zero can cancel off.
Like an answer. I'll make a correct like an answer.
All right.
Yeah.
Send it to me.
Okay.
Does it make sense? Does the answer make sense?
Yes, sir.
Okay, good. Because
Like I'm moving down to
I
because
the
mean,
because
never
D2 is
mind.
supposed to be less than D1, eh? Okay, good.
So at first I thought it was the one I'd see. And so if my working looking like I raise a bit because I rearrange my formula usually to be D1 and then I change it.
Oh,
Understand? But yeah.
Hmm.
let's see. So F1 D1 is equal to F2 D2. So D2 would be equal to F1 D1 all over F2. Yeah, that's correct. Correct.
All right.
Okay, Jaden. It isn't wrong. It's just you might lose some marks because you didn't convert it to meters.
Ew.
Yeah. So let me run through that part, right? So I'm gonna put this full work in, right? So Jaden,
Huh?
input energy is supposed to be equal to output energy, right? You can't just pull out energy from a hat. Remember I was saying that?
Yeah.
Like the 500 joules need to be equal to the 500. I was saying that, right? So why am I talking about that now? I'm talking about that because the work inputted into the system needs to be equal to the output work. The W1 is equal to W2. And that would be F1 D1 because work done, W is equal to F by D. So W1 is F1 D1, W2 is F2 D2. Say what, Masova?
Yes.
I want to find for D2. So I need to divide both sides by F2. Okay, next line. Right? So D2 is equal to F1 D1 all over F2. Now, Jada, when you're doing calculations, you don't have to put the units, right? You have to put the units. So
Yeah.
F1 was 10, D1, D1 I told you was 50 centimeters, right? So let's put that to the side. So D1 is equal to 50 centimeters. So D1 would be, you have to convert that to meters, right, Jadon? If I convert 50 centimeters to meters, what will be?
50 centimeters to meters is 0.5.
Yeah, 0.5. So 0.5 meters. Nice. So I'll say 10 by 0.5 all over F2 and F2. What was F2? Oh no, we're supposed to find for that. Did we find for that? Yeah, we did. F2 was 100 newtons. Right? So when you work this out, you're gonna get 0.5 over 10, which is just 0.05. Wait, let's just plug this into the calculator to make sure. So that'll be 5 over 100, which is 0.05. Yeah, that'll be 0.05 meters. All right, Jiran, let me see what you did. Let's see what you did. So, what was the force? Oh, the force was 20. Oh, oh, my bad. I don't know what I put 10 for. Yeah, that force supposed to be 20. So, my bad. So, 20 by 0.5, right? Over 100. Plug this into the calculator.
0.1.
Right, that'll be 0.1 meters. Yeah, my bad. Right, so
So
that
wait,
0.1
That
meters.
is the exact way to go for doing it,
Yeah.
converting it
This is
to
full.
meters. So if I did it like how I did it, like how I sent it to you, and then in the end I just switch it over to meters, would I still lose marks for not doing it how you did it here?
Okay, if you did that, you would get your full marks because you didn't do anything wrong.
Mhm.
You didn't do anything wrong. But this is just the ideal way to do it. But what you did, what you tell them, is not wrong at all. All right. Yeah, so that's it for class today. The next class, we are going to start thermodynamics. We're going to start the thermal part of physics. How fun. Right. Right, so Jada, now you actually know how hydraulics work.
Yes, I do.
Yeah. So like, you know, all them videos on YouTube, where like YouTube Shorts, where you had these people like crushing things with the hydraulic press.
Mhm.
Now you know how it does work. Yeah. Because I'm sure you'll probably be wondering, well, like, how them creating so much force? Yeah. This is how. So yeah, you have a blessed day. Right? I'll have any
Yes, sir.
Good evening.
what you say, Shana?
Mathvybes, enjoy evening.
Okay. Thank you very much. Right. So later, guys. Have a good day.
Bye, sir.
Bye
Bye,
bye.
sir.